Welcome to a very special edition of ChemVid, where we will be going over the second part of our Lewis dot structure notes, and I will just be going into a little more detail about how to draw these guys and name them and everything like that. Okay? Alright, so the first one is O3. That is also known as ozone. Okay? If I wanted to name it, there are 3 of them, so that would be trioxide, but its common name is ozone. Lewis dot structure, here we go. So I follow the same 4 rules I do for every single molecule. They are all the same. Nobody's special, except for hydrogen, of course. So, oxygen has 6 valence electrons. There are 3 of them, so I'm going to multiply by 3. There we go. 6 times 3 is 18 valence electrons. Alright, now in this case, there's only one atom. So I'm going to put an oxygen in the middle, I'm going to put an oxygen over here, I'm going to put an oxygen over here, and they are going to be bound together. Step number 2. Alright, if I look, I only have 4 electrons used up. So 18 minus 4, that means I have 14 lone pairs, or lone electrons, which need to be put into pairs. So I start with the outside atoms first. So I'm going to do 2, 4, 6, 8, 10, there we go, 12, 14, 16 in the bonds, and then 18 on top. Alright, so in the bonds I have 4, then 6, 8, 10, 12, 14, 16, 18 on the sides. Total of 18, check, done. Used all my valence electrons. Next thing I need to do is I need to check for stability. So if I notice these guys, the oxygens on the sides, they all have 8 valence electrons. 2, 4, 6, 8. 2, 4, 6, 8. So they're good. But this oxygen in the middle only has 6. So I need to share some more electrons. So I'm going to take 2 of these electrons and I'm going to share them with this middle oxygen, creating a double bond. That's okay because I have to do it. I only create double bonds if I really, really have to. And in this case, I do. That's the only way for all of my oxygens to be stable. Now, I could have taken these 2 electrons and made a double bond over here. Totally fine. Same, accurate, all good. Remember that when we have double bonds, that means that we have resonance structures, which means the electrons are moving, and technically both of these guys can be double bonds, and the electrons are just moving back and forth. So either one is good. Alright, then I need to check for lone pairs and see if it bends. Oh, looky here, I've got a lone pair. So this is going to bend slightly right here, and I'm going to have my oxygen is going to look like this. And instead of drawing out the dots, I just drew little lines to symbolize them, which is totally fine. So this is my Lewis dot structure, or this double bond could be over here, and this could be the single bond. Either way, that's how you do it. Now, because these guys are bent down, the shape, or the geometry, is what we call bent. The bond angles for any bent is about 107 degrees. That's on that lovely little sheet that I gave you. And the polarity, if I take a look, because these guys are slightly bent, there is going to be a little bit of polarity going on here. But because they are the exact same element, there's not a lot of separation in charge, so this guy is non-polar. Okay, next one, NO2 minus. First thing I need to notice is that this is an ion, which means that I have 1 extra electron. And I'm going to need to remember to put brackets on my Lewis dot structure. Other than that, it's the exact same thing. So, nitrogen has 5 valence electrons, oxygen has 6, but there are 2 of them, so that's 12. And I have this charge, so that's 1 extra electron. So 12 plus 5 is 17, plus 1 is 18 total valence electrons. Step number 1 complete. Step number 2, put the first atom listed in the middle, connect all other atoms to the side, equal distance apart. Next, add any extra electrons as lone pairs. So I have 2, 4, that means I have 14 electrons left over. So I'm going to do 2, 4 from the bonds, 6, 8, 10, 12, 14. All right, so count them just in case. 2, 4, 6, 8, 10, 12, 14. I have 14 electrons total, which is what I need. Oh, I need 18, silly me. 14 is what I had to add. So I need to add 4 more. After I finish adding a total of 8 electrons to my outermost atom, I need to add 2 to the central atom. So always add to the outmost ones first, then you start adding extra electrons to the middle one, and make sure you add the total amount of electrons, not however many electrons you had left over. That was my mistake. All right, so now I have all of my electrons added. Check for stability. Oxygen has 8, oxygen has 8, nitrogen only has 6. So the only way I can fix this is I'm going to share some electrons. And remember, you only make a double bond if you absolutely have to. I could also use this oxygen and put it over there, but because of resonance, it's pretty much the same thing. So either way will work. Here we go. I've got oxygen with a double bond. And, oops, there we go. Oxygen with six electrons. All right, so now everybody has 8 valence electrons. So we're all good. Now I need to check for lone pairs. I have one. So these will technically be bent a little bit down. So I'm going to do nitrogen. And to save time, I'm just going to draw these lovely lines. Like that. And therefore, I have my Lewis dot structure right there. Oh, but wait! I need to add a bracket because this is an ion. So I'm going to put a little bracket around this and put a negative charge. Now, I am done. All right, so let's look at geometry. This guy is, again, he's bent. And bond angles is about 107 degrees. And polarity, he's bent, but there is a little bit of a separation in charge because the nitrogen's going to be slightly polar. However, there's a little electron pair up here, which means that he is got some negativity up there. So we're going to call this guy nonpolar overall. Okay, last one. BF3, right over here. Follow my rules. Boron has 3 valence electrons. Fluorine has 7, but there are 3 of them, so 7 times 3 is 21. That gives me a total of 24 valence electrons. First one listed goes in the middle. Fluorine comes out. Equidistant apart. Bam, 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 bam. All right. Then I have 2, 4, 6 valence electrons. I need 24, so 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Done. I have all of my electrons used. Everything spread out evenly. I'm ready to go to my next step. I need to check for stability. So fluorine has 8 electrons all around it. So all my fluorines are good. But if you notice, boron only has 6. Now, we may think, oh, I need to make a double bond in order to make sure that boron has as many electrons as he needs. But remember, for every rule there is an exception, and boron is one of those exceptions. Okay? If we look at our periodic table, remember that boron is really small, so he's actually okay with only having 6 electrons. Anything smaller than phosphorus is pretty okay with only having 6 electrons. Anything bigger than phosphorus, like sulfur, can have more than 8 electrons on them. But remember, it's only if they really have to have it that way. So as I look over here, fluorine is very stable and it's very electronegative, so he's going to keep his electrons over here. Boron's okay with only having 6, so I will not be creating a double bond in this case. This one is stable, just like this. Okay, he's an exception. Now I need to look for any lone pairs. Boron doesn't have any lone pairs, so there's no bending. So this has 3 atoms coming off to the sides, which means it's going to be trigonal. And then since there are no lone pairs on the center atom, they are not being pushed up or pushed down. So they lie in a plane, so it's called trigonal planar. All right. What was our next one? Oh, bond angles. For a bond angle, I'm going to look at my geometries. And it looks like if I have 3 guys coming off in equal distant relationships, that means I have a 120-degree relationship. So I would write out 120 degrees for my bond angles. And since these guys are symmetrical and everybody is equally distant apart and everything like that, I do not have a separation in charges, so this is non-polar. Okay, hopefully this video helped you out. Remember, every lone pair, or not every lone pair, every Lewis dot structure follows the exact same rules. So always start from the beginning, follow those rules, and you'll be able to draw any Lewis dot structure I throw at you. Okay? There are some exceptions, but we'll cover those, like boron trifluoride. We'll cover those, and you'll get used to them. But remember, they're only exceptions if they have to be. So I will usually specify. Please come in if you need any more help, and I hope you enjoyed this video.